Hi, folks. We just finished up talking about collisions in terms of energy and energy conservation. Now I want to start talking about momentum. When you hear the term momentum, probably what you think of is something difficult to stop. And that's really a good um, analogy to what momentum is. When something has momentum, it is actually a quantity of a moving object. That's slightly different than inertia, because inertia is a characteristic of any mass, and it's the tendency of an object to maintain its state of motion. So if it's stationary, it stays stationary unless a force acts on it. If it's moving, it stays moving in a straight line unless a force acts on it. And that's Newton's first law of motion. And Newton was really interested in momentum. And in fact, he considered momentum as the quantity of motion. When something has more motion, it has more momentum. And momentum is a formula, a numeric value that is based on mass and velocity. In fact, it's the product of mass and velocity. And the mass is in kilograms, the velocity is in meters per second. It's a vector quantity because velocity has a direction, so momentum has a direction. So if direction changes, momentum changes. If direction reverses, momentum reverses. And that's a big change in momentum when it changes direction. So if we have a change in direction, we need to make sure we specify a positive and negative if it reverses direction. Our formula is P equals mv. The symbol P is used for momentum because M was already used for mass or molarity or molality in chemistry. So they had to use a different symbol. We don't know exactly why they chose P. One of the ideas is that it stands for progress by the physicist Leibniz, who was kind of a contemporary of Isaac Newton, and but there's never been a explanation of why P is used. But P equals mv. Our units for momentum is kilogram meters per second. There's no shorthand unit or no nickname for that. So kilogram meters per second is our units that we deal with. You can see these graphs here. When mass goes up, momentum goes up. When velocity goes up, momentum goes up, and they're linear relationships. So if I double the mass of something, it has twice the momentum than it had before. If I decrease the velocity of something by 5 times, it has 5 times less momentum. Very direct relationship between mass and momentum and velocity and momentum. All right, so here's an example problem. We have a puck, it's got a mass of 170 grams, okay? And it's going at a velocity of 7.7 meters per second. We'll assume that it's positive direction. We don't have any other indication of direction, so that's important. We have to change our mass to kilograms, 0.170 kilograms, because that's our base unit. But to solve this, we can then find the momentum by multiplying mass and velocity. So 0.170 kilograms times 7.7 meters per second, and we get 1.3 kilogram meters per second is our momentum of the hockey puck. Sometimes we compare momenta of different objects. For example, this ball of Play-Doh and the ball of bread dough that are compared, or pizza dough, I should say. They're both moving at the same speed, so velocities are the same. If one of them has more momentum, that means it has more mass. And if we're told it has 3 times more momentum, it has 3 times more mass. Very direct relationship. So the Play-Doh has 1/3 the mass of the pizza dough, or the pizza dough has 3 times the mass of the Play-Doh. And we can use that relationship if we're comparing. This is why it's so difficult to stop a larger guy in hockey or in football. So the bigger the person moving at a certain speed, the more difficult it is to stop. All right. Impulse is defined as a change in momentum. So P equals mv. Sometimes you'll see the arrows there that indicate that these are vectors. we're not going to change the mass of an object very easily, but we can change the velocity. And remember, a change of velocity is called an acceleration. And that acceleration is the change of velocity divided by time. This is where Newton really was looking at stuff. He was looking at changes of momentum caused by forces. Now, obviously, when we change momentum, we're putting a force on something. So a force causes an impulse. The force and the impulse are not quite the same. Don't get confused by that. Now, remember, we already talked earlier in the year about forces for a certain distance cause a change in kinetic energy. We used the work kinetic energy theorem. Work is force times distance equals 1/2 mv final squared minus 1/2 mv initial squared. Well, m and v give us kinetic energy. They also give us momentum. Different formula, but a force causes a change in kinetic energy by the work kinetic energy theorem. Let's look at impulse momentum theorem. An impulse happens when a force acts for a certain time, not a certain distance like in work. So an impulse happens over a time period. Now, this is where Newton first came up with the idea of a change momentum, F equals m delta v over delta t. Now remember, delta v over delta t is acceleration. So Newton was really focused on changing momentum. Now we've changed that to F equals ma over the course of years. He didn't talk about acceleration. He talked about a change in momentum. So if we multiply both sides by delta t, we get this. Force times delta t equals change in momentum in the blue here. That could be written as mv final minus mv initial, either way, okay? But that is what an impulse is, a change in momentum. Now, here's the thing. And when we ask what is the impulse, if you know the mass of the object and its initial and final velocities, you can find the impulse very easily by finding the change of momentum. We can also find the change in momentum if you know the force and the time. A force over a certain time period will change momentum. So impulse is force times time. This is the whole concept behind seatbelts and airbags. If you can increase the time, you can decrease the force. So if you are in a car accident, you're going to come to a stop. Your body's momentum will change no matter what, and it will have the same impulse, the same overall change of momentum, whether it comes to a stop in a very short amount of time or a very long amount of time. Now, in that time period to come to a stop in a car accident, it's very short no matter what. But if you would come to a stop in 1/100th of a second or come to a stop in 1/10th of a second, well, 1/10th of a second is 10 times longer than 100. So by increasing the time 10 times, you decrease the force 10 times. That can be a matter of protecting your body from serious injury by decreasing the amount of force that you have to absorb by a factor of 10. Even though it still only took 1/10th of a second to stop, it's 10 times more time, so 1/10 the force. So the impulse is the same. The change of momentum is the same. So don't think of force as a change of momentum. Force times time is change in momentum. So if we increase the time, we decrease the force. All right. So here's an idea behind this. If we look at these people, if you've ever been in an egg toss contest or a water balloon toss contest, you know that if you catch the egg or the water balloon with rigid hands, it's going to break and you're going to lose. So you want to give and bring it to a stop over a shorter period of time, or I'm sorry, a longer period of time to reduce the amount of force. Now, this video shows these kids in a classroom throwing an egg at a sheet, and the egg hits the sheet, and it puts a small amount of force on it for a longer period of time, and that reduces the amount of force so the egg is not broken. Now, this didn't work for me last time, so let's see if this works. No, it doesn't want to work. So let's do this. And there we go. So you can see here, he's throwing it at this.
Anytime.
And here he misses the whole sheet, hits the wall. We got egg on the wall. That's a problem. All right. So you can see this question here. If one applies the brakes to a car with double the force over the same amount of time, what will happen to the car, impulse of the car? Well, if we double the force over the same time period, the impulse will double. All right. So he will come. The first assumption is this didn't come to a stop the first time. All right. Okay. So we got this final math check. Now, I have a Socrative. So if you're watching this, I have a Socrative running. So please try the Socrative out to check and see how you're understanding this stuff. If you're in class, obviously you're not watching this, so you're going to do the Socrative in class. But here's another couple checks. We have a kickball. We know the mass of the kickball is going east at 5.44 meters per second. And now it moves west at 7.88. Direction's important. You need to make sure one of these is positive, one of them is negative, because it reverses direction. It didn't just go from a speed of 5.44 to a speed of 7.88. That would mean speeding up, and it would have a change in velocity of 2.44 meters per second. No, it changes velocity radically, like 12.88 meters per second, because it reverses direction. So I'm going to make the west positive and the east negative. All right, so treat everything in relation to westward direction. So the impulse of the ball is to change of momentum. So we can just find the change of momentum by taking the mass of the ball and the change of velocity. And it's 21.2 kilogram meters per second. It would be wrong if we did this, 2 kilograms, 7.44 minus 5.44 equals delta P. Okay, that's wrong because that's only a change of 2.4 or 2. Well, first of all, we didn't do that right. That's 7.88. Okay, but you need to take into account the change in direction. So we know that the impulse right here. Now we also know the time. So remember, force times time equals change in momentum, 21.2 kilogram meters per second. So now we can do that and find the force that was put on that ball, 141 newtons. Because kilogram meters per second divided by seconds is kilogram meters per second squared, which is the same as newtons. All right. So do the Socrative. We do have some homework problems for you guys to work on for the next day here. And then after that, we're going to start talking about collisions in momentum terms instead of just energy terms. Hope that works. Thanks a lot, guys.